Let's take a look at question 6 for the electromagnetism. Here's a glass U-tube containing liquid sodium which conducts electricity. Okay, so what happens is that a current flows through the sodium. So this is the direction of current flow, I. And then there's a magnetic field, okay, B, pointed into the page. So let's take a look at what's actually happening to the sodium. Now, here is the current I, and then there's a magnetic field B. If you draw the left-hand rule, if you draw Fleming's left-hand rule, okay, this is kind of like what you will get for Fleming's left-hand rule. First of all, the current is upwards, so the middle finger is pointing upwards. Next, your pointer finger is pointing into the screen. Then after that, your thumb is pointing to the left. Alright, so this is how your Fleming's left-hand rule will look like. Now, what this means is that for every part of the sodium metal that is conducting electricity, it will be pushed to the left. It will be pushed to the left. So what happens is that the sodium level rises on the left-hand side and drops on the right-hand side. Okay, now this is causing all the liquid sodium to actually displace to the left, okay, pushing against the weight of the sodium on this side. That's quite substantial. Right, so let's calculate the force acting on the liquid sodium due to the magnetic field. Now, using force is equals to BIL, alright, the magnetic flux density is 0.12 Teslas, the current is 80 amps, and the length of the sodium current is 2 cm, so put 0.02. So there's a force of 0.192 newtons along this entire length of the current. So if I draw the U-tube like this, alright, and then I imagine that there's an imaginary current on this side, then the force of this current is 0.192 newtons. Okay. Now, what happens is that this force is exerted on every part of the sodium inside the U-tube. Now, I'm going to take some time to draw for you, okay, what the U-tube might look like. Right? I want you to imagine this U-tube here has a rectangular cross-sectional area. Okay, so there's a rectangular plate, rectangular face of the sodium current on this side. Now, the force acting on this plate, will be 0.192 newtons to the left. Now, we know that this force is going to cause all the sodium to rise up, okay, in this place. That means that it creates a pressure. This 0.192 newtons creates a pressure that causes the sodium to the left. Okay, so it's an excess pressure to the left. Now, so how much pressure is it? Now, we know from the equation that pressure is equals to force over area. So the additional pressure created by this force will be 0.192, and this is 2 cm, and this is also 2 cm. So this is a 2 cm square area over here, which is 2 cm by 2 cm. So this is 0.02 times 0.02. Now, this causes a pressure of 480 pascals. So what will happen is that it will cause an additional pressure of 480 pascals on the sodium to the left. Okay, right. So the additional force causes a pressure of 480 pascals to the left, which means that this whole surface will be lifted up, okay, until this point here will be atmospheric pressure plus 480 pascals more. Right, and this point here is atmospheric pressure. Now, this point of the sodium, the pressure of the sodium is given by H rho G. So we know that the additional pressure here, H rho G, or rather rho GH, will be equals to 480 pascals. Okay, additional pressure. So then we can just substitute in the values for rho G and H. to determine that the H will be 0.051 meters, or rather that it will be lifted up by about 5.1 cm. Okay, so this is how to calculate the pressure on the sodium column. Okay, the entire sodium is shifted to the left because of the force exerted by the magnetic field. Now let's move on to question 7. Now question 7 is about current balance. A wireframe is supported on a knife edge so that the section PQ lies in the solenoid and there's a spring. Given that the magnetic flux density inside a long solenoid is mu naught Ni, calculate the magnetic flux density in the region PQ. Alright, so PQ is having a force downwards. Alright, and the magnetic flux density is due to the current 3.5 amps, and don't forget there's a solenoid, the solenoid has 700 turns per meter, which is a small n. Okay, so what's the logic inside here? The solenoid creates a magnetic field inside the solenoid B, and then due to this, the current PQ experiences a force downwards. Now the force experienced by PQ will be equals to BIL. Right, now how do you calculate the B? The B is calculated using mu naught I. Mu naught Ni of the solenoid. Okay? Then you multiply it by the current, which is IPQ. Then you multiply it by the length of PQ. Right. So let's fill in all these values here. FPQ is equals to, then we can fill in mu naught I, which is shown over here. Okay. So 4 pi times 10 to the power of 7 times 700 times 3.5. So the magnetic flux density B will be equals to 3.1 times 10 to the minus 3 Teslas. So based on this, the side PQ has a length 5 cm. So calculate the force acting on PQ due to the magnetic field in the solenoid. F equals to BIL. That will be 5.4 times 10 to the power of minus 4 newtons. Okay. Now the last part of this question is about moments. So I've copied over the diagram over here. Now I'm going to draw the wire over here. This is the F magnetic force. This is the tension from the spring. So the magnetic force we've calculated is 5.4 times 10 to the minus 4 newtons. Alright, this length here is 10 cm, and this length here is 6 cm. So they're asking us what is the spring constant K. Now T is equals to Kx. So using the principle of moments, alright, Fb times 0.1 will be equals to Kx times 0.06. So if we fill in the values, 5.4 times 10 to the minus 4 times 0.1 equals to the spring constant multiplied by the extension 0.5 cm multiplied by 0.06, and that will give us the value of the spring constant K. K is equals to 0.18 newtons per meter. Just 0.06 over here. Handwriting was not so clear. Alright. Now, let's take a look at question 8. Now, in question 8, we have 3 long parallel wires that attract and repel each other, and we're supposed to find the resultant force per unit length experienced by Z. Now, let's take a look at the concept for this question, is that parallel currents attract each other, while anti-parallel currents repel each other. Now, so if we take a look at Z, we are supposed to find out Z. Now, Y repels Z, so this is the force of Y. But X attracts Z, this is the force of X. So now we will have to find out what is the force of X and force of Y, and then subtract them from each other. But before we do that, let's take a look at the relative comparison between Fy and Fx. Now Fy is repulsive, so it's downwards, and it's larger than Fx. Now the reason is because Fy is closer. Y is closer to Z, and it carries a larger current than X. So clearly that Fy will be stronger, therefore the net force on Z should be downwards. Okay, now let's take a look at how do we calculate Fx and Fy. In general, the force between two wires, for example Fy and Z, will be equals to mu naught over 2 pi. Alright, then we multiply by the current of Y, then multiply by the current of Z, and then multiply by the length of the two wires. Now, however, the length of the wires is not given and is said to be very long. So what this means is that actually we can the question instead asks us for the force per unit length. So we take Fyz divided by L. Okay, so this is what the question wants. All we're going to do is work out these values on this side. So the question has kindly substituted for us. We are finding Yz first. Okay, so Yz will be over here. Alright, mu naught over 2 pi multiplied by current in Y, current in Z, divided by the distance between them. It gives us 4 times 10 to the power of minus 6 newtons per meter. It's newtons per meter because it's the force per unit length. Now in the same way, we can write Fxz over L will be equals to mu naught over 2 pi multiplied by Ix multiplied by Iz. Okay, and that will give us 1 times 10 to the power of minus 6 newtons per meter. Now, so we know that the force on the wire Fyz is downwards, and the force on the wire from Xz is upwards, and Yz will win. So what this means is that the net force, okay, per unit length will be equals to 4 minus 1 times 10 to the power of minus 6. This will give us 3 times 10 to the power of minus 6 newtons per meter, and it is in a downwards direction. Alright, so let's look at the answer over here. The wire is infinitely long, so we calculate the force per unit length. The force per unit length by X on Z will be upwards, 1 times 10 to the minus 6. And the force by Y on Z per unit length will be 4 times 10 to the minus 6 downwards. So the resultant force per unit length will be 3 times 10 to the power of minus 6 newtons per meter downwards. Alright, so please do specify not only the number but the direction of the force. Now in question 9, we have a spring which conducts electricity. The circuit is closed. The battery will push wire into the spring. Okay, so we draw the arrows in this direction. Notice that in every coil, the current flow in the same direction. Okay, and so basically the coils carry parallel current. Okay, so the direction of the current in the individual turns of the spring are as shown over here. Now draw the pattern of the magnetic field due to a straight current carrying wire. We draw a small circle first, then we draw a larger circle, and then we draw a largest circle over here. Okay, please try your best to draw concentric circles. Now, using the answers in A and B, explain why the spring changes in length when the current is switched on, making reference to the current, magnetic field, and force experienced between the loops of the spring. Now, in the coils, the current flows in the same direction, so basically the coils carry parallel currents. Now, if we draw another wire on this side, carrying current in the same direction, then by Fleming's left-hand rule, the force will be to the left, FBI. So what we say is that as the coils create a magnetic flux, field flux density around them, by Fleming's left-hand rule, the force on parallel currents is attractive. Right? So parallel currents tend to attract. This means that the coils tend to attract each other. Hence, the spring will shorten. Alright? So this is basically the answer. Alright, the coils carry parallel currents, and parallel currents attract each other by Fleming's left-hand rule, so the spring will shorten. So you explain why the spring changes in length when the current is switched on. In the coils, the current flows in the same direction, so the coils carry parallel currents. As the coils create a magnetic flux density around them, by Fleming's left-hand rule, the force on parallel currents is attractive. This means the coils tend to attract each other, and hence the spring will shorten. So we need to see the following answers. That number one, there's a parallel currents. By Fleming's left-hand rule, parallel currents attract each other, and hence the spring will shorten. I want to see all these 3 points, okay, in order to get them up. The spring is compressed as the spring's length decreases. Okay. Alright, and that's question 9.